Welcome back to the deep dive. We've sorted through that stack of sources you sent, including that really striking analysis, why big tech is going nuclear, and we've tried to pull out the essential truth from, well, all that data. Our focus today, it's the engine room of the future economy, really. Energy infrastructure, because the AI boom, its relentless appetite, it demands massive computational power. And that's creating this unprecedented surge in energy use for data centers, the grid we have now. It just isn't built for this kind of rapid, super dense growth. What we saw across all the materials seems pretty clear. AI's energy needs are forcing big tech to completely rethink its power strategy. And this makes nuclear energy, specifically these next-gen fission reactors, a really crucial piece of future digital infrastructure, despite all the history and the politics around it.
Yeah, it's really moves beyond preference or even just hitting decarbonization targets, although those are still factors, of course. This is becoming an operational necessity. I mean, you're seeing huge players, Amazon, Microsoft. They're not just buying power anymore. They're actively investing, planning, hiring actual nuclear expertise for their own facilities. The scale of demand is so huge, they're essentially getting into the power generation business themselves now.
Okay, let's unpack that scale a bit. We get that AI is power hungry, but why is it happening so fast? Why are these massive companies suddenly facing a power crisis? What's failing them with the traditional grid right now?
Well, it's a mix, really. It's the speed of growth, yes, but also the power density. Training these huge language models, running complex cloud services, handling millions of AI queries all at once. It takes incredible computing power, running 24/7. And all that energy consumption is packed into these relatively tiny physical spaces at the data centers. Just look at those projections we saw. Global electricity demand from data centers, it's set to more than double by 2030.
Double. Wow.
Yeah. Think about that. In just 6 years or so, we're adding the energy demand equivalent to, like, multiple medium-sized countries, just for digital stuff.
And it's not spread out evenly, is it? It's concentrated near cities or these big fiber optic hubs, which puts just enormous strain on local power grids that were, frankly, designed decades ago for much slower, more distributed growth.
Exactly right. And even if a local utility could eventually build out the capacity, the timelines just don't match the speed AI is moving at. Data centers needed that power yesterday, basically. But even if they could build, say, enough solar or wind farms quickly enough, they still hit that intermittency problem.
Right. Renewables are great. They're clean. But they aren't always on, not continuous.
And data centers need what we call firm power. They absolutely cannot tolerate a dip or a fluctuation because the sun set or the wind died down. Any interruption could mess up critical services worldwide. And while big batteries are getting better, they're still really expensive and honestly can't guarantee that 24/7 reliability for the kind of baseload power the AI industry needs, not at this scale.
So nuclear steps in. It offers that baseload power, reliable, dense, carbon-free, always on.
It's pretty much the only scalable, dispatchable, carbon-free source that really fits their immediate massive needs right now. For big tech, not having guaranteed power isn't just, an annoyance. It's an existential business risk. If they can't power their growth, they could lose the whole AI race. That's why they're being pushed to vertically integrate, essentially becoming their own power producers.
Okay, we absolutely have to address the elephant in the room here. You say nuclear, and I know for a lot of people listening, their minds jump straight to, well, 3 Mile Island, Chernobyl, maybe even weapons. Big tech going nuclear definitely sounds alarming at first hearing.
Oh, completely. It's a totally understandable reaction, given the history.
Yeah.
But it's so crucial to understand the fundamental difference between modern commercial nuclear power and nuclear weapons.
Right. We need to clarify that distinction. Not just with, percentages of enrichment, but conceptually. What's the core difference?
Okay, it boils down to the mechanism and the intent. A nuclear bomb is engineered for one thing: an uncontrolled, incredibly rapid runaway release of energy. To do that, it needs very pure, highly concentrated fissile material. Think weapons-grade uranium or plutonium. It's like using highly refined jet fuel designed to ignite instantly and explosively.
Okay, maximum bang.
Exactly. Whereas the nuclear reactor is designed for the complete opposite. It's built for a controlled, slow, steady release of heat, sustained over years, even decades. It uses fuel that's only slightly enriched, usually around 3 to 5% radium-235. That low enrichment level makes a runaway explosive reaction physically impossible. And the key safety mechanism is the control rods. These are always present in the core, absorbing excess neutrons, actively preventing the chain reaction from ever accelerating out of control. So the bottom line is, A commercial power reactor simply cannot achieve the conditions needed to explode like an atomic bomb. They are fundamentally different things.
So the physics and engineering of a power reactor are actively designed to prevent it from behaving like a weapon. That helps address the historical fear, definitely. But the specific tech big tech is looking at, these small modular reactors, or SMRs, they're still relatively new to the public eye. Why SMRs? Why not just build the giant reactors we're used to seeing?
SMRs are a really significant leap, almost tailor-made for this problem. First, just their size. They're small enough to be largely built in a factory, then shipped to the site. This means they can be sited much, much closer to the actual data center hubs.
So you bypass the need for building hundreds of miles of massive new power lines.
Exactly, which, as you said earlier, is a huge regulatory and cost barrier. It simplifies siting dramatically.
Okay, convenience, location. Makes sense.
But the real game changer, I think, is the safety design. These aren't just miniature versions of the old large reactors. SMRs typically utilize what are called passive safety systems.
Passive safety, what does that mean in practice?
It means that if something goes wrong, like a loss of power or some kind of system malfunction, the reactor doesn't rely on active measures like pumps needing electricity or human operators having to flip switches to shut it down safely. Instead, it relies on fundamental forces of nature, things like gravity, natural convection, pressure differences to automatically shut down the reaction and keep the core cool.
So it fails safe, basically, by default.
Precisely. It's designed to fail safe every time, without needing external power or immediate human intervention. This drastically reduces the risk profile compared to older designs, particularly for major accidents like the ones that loom large in public memory.
That sounds like a compelling case for the tech itself, necessity driving innovation towards safer designs. But let's pivot now to the necessary ethical discussion here. You mentioned earlier that this sudden scramble for power, for viable, maybe cheaper options, could have serious global knock-on effects.
Yes, it absolutely raises some critical ethical flags we need to watch closely. When big tech moves fast, they often look for what some sources call fast land. Essentially, locations where the regulatory hurdles are lower, maybe environmental opposition is weaker, permitting is quicker.
So the concern is, are they potentially looking to site these very sensitive, very expensive nuclear facilities in developing countries, specifically to bypass the tougher environmental reviews and public scrutiny they'd face in, say, North America or Europe?
That's the core concern, yes. While putting a data center or even an SMR somewhere might bring local investment, there's a real risk of creating an unequal burden. Big tech could potentially exploit weaker environmental protection laws or less stringent regulatory oversight. This could lead to long-term environmental problems if waste isn't managed perfectly or if safety standards aren't upheld to the highest degree. It's a kind of potential regulatory arbitrage.
Okay, but playing devil's advocate for a second. Wouldn't the sheer hassle and regulation involved in transporting nuclear fuel to the SMR and then managing the spent fuel from it, wouldn't that be so heavily scrutinized in their home countries, like the US or Japan, that it would just make more sense to build these things domestically, close to existing nuclear infrastructure and expertise?
That's a very fair point. And yes, the regulatory burden around moving nuclear materials is immense. It's not trivial at all. However, sometimes the combination of lower land costs, much faster local permitting, and perhaps specific tax incentives offered by a host nation can potentially outweigh the complexities of fuel transport and management, especially if speed to market is the absolute top priority.
Speed driving decisions again.
Right. If getting the power online 6 months faster gives you a critical edge in the AI race, the incentive to find the path of least regulatory resistance, wherever it is, becomes very powerful. And that's why their success, their social license to operate here, really hinges entirely on preempting these fears. They need to demonstrate extreme accountability and transparency from the get-go.
Okay, so how do they actually prove that accountability? What tangible steps do they need to take, especially regarding global governance? It can't just be a press release saying, we care.
No, absolutely not. First, they have to commit to strictly complying with and ideally exceeding the highest global safety standards, not just the local minimum. That means engaging very early, very openly, and very deeply with international regulators like the IAEA, the International Atomic Energy Agency. They can't just design something and ask for approval later. They need to proactively demonstrate that their SMR designs and their planned operating procedures meet or beat the toughest international benchmarks, regardless of the host country's specific laws.
And presumably, this transparency extends to their workforce, too. Because running a nuclear facility requires highly specialized labor working in potentially hazardous conditions.
Absolutely crucial. They must guarantee fair and safe treatment for all workers involved globally. This means implementing the highest international standards for labor practices and, critically, for radiation dose limits for workers. Again, this standard has to apply regardless of what the local law in the host country might allow. They have to basically import and enforce the highest global safety culture everywhere they operate. No cutting corners just because local labor protections might be weaker.
That commitment, highest global standard, worker safety, regulatory compliance, transparency, that really seems like the defining line. It determines if this whole shift is viewed as necessary innovation or, well, a corporate shortcut with global risks. All right, let's look longer term then. Given how reliable nuclear is it likely to become the single main power source for big tech? Will it effectively replace everything else in their energy portfolio?
Probably not. Unlikely to be the single source. What we're likely to see is a continued hybrid energy mix, but with nuclear playing that absolutely critical role as the baseload, the firm power component. They know diversity is key. Right? It protects against any single point of failure, whether that's a technical issue, a regulatory change, or even a fuel supply problem.
A mix makes sense.
And what's really interesting is how these SMRs are being designed to actually work with renewables, synergistically. Many SMR designs have flexibility built in. They can do what's called load following. Meaning when your renewables like solar panels on a sunny day or wind turbines on a windy one are generating a ton of power, the SMR can automatically dial back its own electricity output. It might even divert its excess heat for other uses, like making hydrogen fuel or district heating or industrial processes. This kind of cooperative approach, it significantly reduces the need for those massive, expensive battery farms we talked about earlier to smooth out the intermittency of renewables.
Ah, okay. So the SMR acts like a stabilizer and a partner for renewables, not just a replacement. That makes the grid much more manageable. What other clean, firm power sources are they looking at for this future mix, besides fission SMRs?
Yeah, they're definitely hedging their bets and investing in complementary firm power sources too. Next-generation geothermal energy is getting a lot of attention and investment.
Because it's also continuous, right? Like nuclear.
Exactly. It's another 24/7 carbon-free source. And then looking further out, maybe a decade or more, you see them making strategic moves like signing future power purchase agreements for nuclear fusion. Fusion is still very much developmental, but it holds that promise of virtually unlimited clean energy with significantly less long-lived waste compared to fission. So they're investing across the board, near-term, medium-term, long-term, firm power.
Covering all the bases. Okay, this brings us neatly to big tech's unique contribution here. Their core expertise isn't nuclear engineering, it's data science, AI, managing incredibly complex digital systems. How does that expertise translate into making nuclear power safer? And I think you used the term smarter.
This is where their background could genuinely bring huge value to the nuclear industry, which, let's be honest, has historically been a bit conservative, maybe slow, in adopting the absolute cutting edge of digital management. Big tech lives and breathes processing gigantic streams of sensor data in real time to optimize everything: server loads, cooling efficiency, network traffic.
Right.
So now they're applying that to reactors. First is real-time monitoring. Imagine thousands upon thousands of sensors constantly tracking temperature, pressure, coolant flow, neutron flux, vibration, everything throughout the reactor system. AI models can ingest and analyze these massive continuous data streams far more than any team of humans could possibly watch to detect tiny, almost imperceptible operational anomalies or deviations long before they could ever become a safety concern.
So it's like predictive safety, finding the warning signs way earlier.
Exactly. Finding the needle in the haystack that indicates something might start to go wrong down the line. It's proactive, not just reactive.
Okay, applying data center optimization logic to reactor physics. Interesting.
And that leads directly to the second part, predictive maintenance. Traditional power plants, including nuclear, often relied on scheduled maintenance. You replace a part every X years, whether it needs it or not, or you wait for something to break. Big tech's AI, using machine learning on all that sensor data, can predict with much higher accuracy when a specific component, like a valve or a pump, is actually likely to degrade or fail. This lets them schedule maintenance exactly when needed, which reduces operating costs, boosts the plant's overall uptime, and most importantly, prevents unexpected shutdowns or failures that could potentially raise safety questions.
Makes sense. More efficient, less costly, and safer because you're fixing things before they break. And you also mentioned digital twins. What exactly is that? It sounds like creating a virtual copy of the reactor.
That's precisely what it is. A digital twin is a highly realistic, dynamic, constantly updated virtual model of the physical SMR. It mirrors the real thing in real time. Big tech already uses this concept extensively to model and optimize their data centers, airflow, temperature, power usage. They simulate changes virtually before implementing them physically.
Okay.
Now, they're applying that same simulation expertise to reactor physics and operations. This lets operators run incredibly complex what-if scenarios, maybe simulating equipment failures or different operating conditions, or even practicing emergency response procedures, all within the safe virtual environment. They can test and refine control algorithms, optimize performance, even train AI systems for autonomous operation or maintenance tasks, all without ever putting the actual physical reactor at risk. It's a huge step for both safety validation and performance optimization.
Wow. Okay, this has been a genuine deep dive, hasn't it? We've pulled together the technology, the economics, the global ethics. We've covered the sheer speed and necessity driven by AI's energy demand, the specific safety advantages of these new SMRs, the absolute requirement for global ethical standards and transparency from big tech. And finally, how their own expertise in AI and data might actually make nuclear power smarter and safer in the future through things like predictive maintenance and these digital twins.
Yeah, I think the synthesis, the main takeaway, is pretty clear. Nuclear energy seems almost inevitable now as a powerful solution to the AI energy crisis, mainly because of its unique reliability and power density. But its ultimate success, and crucially, its acceptance by the public globally, depends entirely on matching that technological innovation with absolutely unimpeachable ethical business practices and complete transparency. The tech alone isn't enough.
Well said. And that leads us to one final thought for you, the listener, to maybe mull over as big tech pushes forward with these nuclear ambitions, potentially accelerating SMR deployment worldwide. If their drive does successfully speed up the global adoption of fission technology, well, society then has to confront the fact that we are also accelerating the creation of high-level nuclear waste. And that brings forward the universal, very long-term challenge of its final disposal, a problem that, frankly, very few countries on Earth have a truly permanent, agreed-upon solution for right now. So the question to leave you with is, what's our collective role? What's your role in understanding and grappling with that accelerating long-term responsibility? Something to think about. Thanks for diving deep with us today. We'll catch you next time.